Awesome. Are we just good?
Yeah.
Awesome. Hello, everybody. Welcome to the second part in this series where I actually explain how to do things. Great, we love it. Cool. Announcements. We don't have meetings next week because we're going to be off for like SIGPwny and a bunch of other stuff is going on that weekend. So we're giving y'all a break. Also fill out the feedback form, please. We are doing research for like a class and it's important and we want as many responses as possible. So if you haven't filled it out, you should. Thanks. I'll wait for you. The link is also on like the Discord a bunch of times, I believe. And if someone wants to publish it in general, they should. All right, so this is a meeting flag, and a very funny PCB as always. I don't know if the meeting thing has been published yet, but if it hasn't, it will be up soon. Cool. So before we start, I'm going to go into a little bit of background on what AI is, how we create an AI model, just so that people have an idea of what that looks like. And how, like, all these things that create an AI model can be used to exploit the created model after it's created. So what is AI? Everyone talks about AI models. You know, there's a lot of discussion about various aspects of AI, but fundamentally, what is it, right? Like, do we know? It's math. It's all just math. It's all, like, it's calculus, it's linear algebra. At the end of the day, it's just computers doing math really, really fast. A lot of statistics too, but it's all math, and we can use kind of how the math works to exploit it. So for a more serious explanation, this is what an AI model or like a deep learning model looks like at a very like microscopic level. So you have what are known as neurons, and they get connected. And like you can connect up like a lot of them to create what is known as a neural network or a deep neural network. And that's the basis of like all a lot of complex AI models that you see today. So like your ChatGPT, your whatever, your classification models, your Midjourney, they're all at the end of the day neurons that have been trained and have like some sort of weights and biases. And I'm massively oversimplifying all of this. Like this is like your 5-minute explanation instead of your like 2 million hour explanation. But at the end of the day, that's what it is. And all these neurons, when you put them together, they form basically what is a graph. And this graph here, it's like a 4D representation. AI models are like 2 million dimension graphs, right? Like they are like you can't. There is no way to like form a pretty graph like it is here. But at the end of the day, that's what it is. It's a graph that has local minima, local maxima, and it's just a big graph that has the problem that you're trying to solve. And why I'm giving you this like graphical idea of like AI models at the end of the day are just graphs that can perform very complex things. And the reason I'm telling you that is because that's integral to how we create AI models, right? So how many of y'all like remember like gradients and stuff like that from like calculus, right? Yeah. Okay. Cool. So at how we create AI models is we perform gradient descent, right? Which is given your graph, your however big complex graph, you have the gradients of the graph, which is how we get to the local minima. And you're performing optimization on this problem. So given a place that you start out from, you want to try and find the local minima. That's the place where there is no error, right? So where your AI model is not making any mistakes, it's doing its tasks perfectly, that's the global minima. And you're trying to find that by just like, you are at some place on the graph, and you are stepping down it by performing gradient descent. And there are various parameters you can set how fast you step down the graph. That's your learning rate. At the end of the day, you are just doing that to try and minimize error. And that is usually how AI models are trained. You can use various parameters to determine what error is, how much error you have. You can look at all of that. And so you have a training data set, right? That's like however much data you collected that explains the problem you're doing. So I'm going to be using classification a lot as an example. So say you have an AI model that can tell you whether something is a dog or a cat, right? You're going to have like a bunch of pictures that are like, this is a dog and this is a cat. That's your training data set. And what you do when you train is you iterate over this training data set multiple times, however many, each time is known as an epoch. And you can have 20 epochs, 50 epochs, a million epochs, whatever. It just depends on how long you want to wait for a model. And at some point, like, your model will be good enough. And you use what's known as a loss function to determine the performance of a model, right? So a lot of times it's like cross entropy loss, or these are various criterions that you can use, and it just defines how well your model is doing. So higher loss means that you have more error present. It's farther off from where it's supposed to be. So like if your model is only getting 25 out of 100 images right, it will have a higher loss than if it's getting 80 out of 100 images right. And that's one of the many like important metrics that you can use to kind of determine how well your model is doing. And you try to optimize this loss, and that's part of what forms that big graph. Is given a loss function, it's doing better at some places than others, and that is just how well your model is doing and how many things it's getting. Again, very, very simplified explanation, but this will help you make more sense of the stuff I'm saying later. Cool. So what is it like? How can AI models be insecure? So if you'll remember on Thursday, I was talking about like the many definitions of AI security. I'm going with the one that is how the models themselves can be insecure. So how can you attack an AI model? What are various ways you can cause it to misbehave? So the first big overarching section is dataset issues. So you may just have a problem with your dataset. Your data may be mislabeled, it may be pre-processed wrong, it just may be incorrect in some way. And that means that the model doesn't know what data is good versus what data is bad. So if you put in garbage data, you're going to get a garbage model. It's performing incorrectly. It doesn't, it's only learning the patterns you give it. So if you give it incorrect patterns, it will learn incorrect representations. There may also be malicious data in large data sets. So we'll get into this later, but one of the attacks that I'm going to be talking about is if your attacker has access to your data set and they can put in like some sort of malicious data, they will be able to make your model perform in ways it shouldn't. So if you're collecting data off the internet and you aren't sanitizing your data, you may end up with some not so great data, and that may impact how your model functions. The other big overarching category is model issues. So this is after your model has been trained, right? So models can be vulnerable to malicious inputs, so stuff that it hasn't seen, or adversarial examples, which I will go into like what that means later. And they may also be vulnerable to extraction or trojaning attacks. So if you have a private model, there are ways that an attacker can use the information you put out into the public to create their own version of a model, and then either distribute it or use that model in combination with other attacks to just like make your model misbehave again. Cool. So first big category is the dataset issues I was talking about. So this is known as dataset poisoning. So you had a good dataset, and then some bad data has been injected. Now your dataset is poisoned. So again, like I said, this is malicious data that is present in a dataset during training. So the model learns incorrect information. This is only possible if your attacker has access to your training dataset. So you're collecting data off the internet and haven't sanitized it, or like you're using some form of human feedback and there may be like a malicious person involved. But this is only during training. Like once your model is created, you can't really have dataset issues because like you're not training again on that dataset, maybe. So this is again also important to consider in situations where the model is trained using human feedback because you may have a malicious human involved. What is a great example of this is the glaze attack. This is something that came out really recently, actually, and it's designed as a way for artists who don't want their art involved in like training the game to have some measure of control as to whether their art has been involved in the training of a game. And what it is given some artwork that you want to put on the internet, but you don't want like some person who's like web scraping like all the art available on Google to train again using your artwork, right? But you still want to post it on the internet so that your friends can see it, like the people who pay you can see it, et cetera, et cetera. So given that you haven't given permission to anyone, how do you post your artwork on the internet and still have it not be involved in training the game? So one way to do this is to cloak it using the glaze technique. And what that means is if someone, you doctor your image in really imperceptible ways. But if someone tries training again on it, your data has now poisoned the data set. And so if they train on your cloaked artwork, which you posted to the internet, once they train it, their game will fail to mimic your art. It will be poisoned. And that's because this is actually bad data, right? It isn't an accurate representation of art, and it is designed instead to adversarially mess with the game. What's up?
Is this cloaking process specific to a model, or is it generic?
So I'll get into this a little more later, but a lot of attacks are transferable to a degree. So like there may be GANs, like now that this attack is out, that have figured out some way to not be vulnerable to a cloaking attack or the blaze attack. But a lot of GANs may be vulnerable, especially ones that are currently being trained and don't know about the glaze attack. This is designed to be as generic as it possibly can be. But again, like a lot of GANs are different, and like some people may start like being very cautious of like the glaze attack and try to figure out ways to defeat it. What's that?
So when you cloak the artwork, are you changing the file type? Like for example, like if we have a PNG, if we cloak that, is it still going to be a PNG for everybody, or would it be a different file?
Yeah, so these are really imperceptible changes. So they're designed to it will still be an image that you can share on the internet, whatever. Like if you look at it on Twitter, it's going to look the same. Like these two images look the same. But you add in like really imperceptible changes to the image that are crafted in a way to like mess up again as much as possible, basically. So it starts learning just incorrect patterns. And those patterns just mess up the artwork that it produces.
Would compression like mess with this?
So maybe I'm not entirely sure. I have seen like people claim that like, oh, like compression doesn't matter. You can like print out like attacks and they'll still work. I'm hesitant as to some of these claims. Like again, like Blaze is super new. Like it was probably released like a month ago. So I think people have like they're still like a discovery phase with like attacks like this, because the first like big product I've seen that kind of works in this way. Because it's like trying to deal with a very new problem. But I'm like I would think not, but it just depends. If that makes sense. Cool. Next big topic, and this is like, so dataset poisoning is not as popular because you have to be in the dataset, right? So like a lot of the problems that are a lot of the ways in which it is effective is if you're web scraping off the internet and not checking your data, or in stuff with like RLHF, which is reinforcement learning with human feedback, where it's like you have a human involved in the process who may or may not be malicious. But evasion attacks are like the most well-researched of kind of the three areas of attack I'm going to talk about. And what they are is malicious input designed to fool a model into undesired behavior. So in the case of like a classification model, say you have like a dog versus cat model. You give it a picture of what looks like a cat, but it actually classifies it as a dog, right? And in the case of like a toy model like that, obviously like this doesn't matter as much. Like who cares if your model is wrong once or twice? But these attacks are designed to be like designed to work basically all of the time. So your model now has like a 3% accuracy instead of a 90% accuracy. And obviously with toy models and toy problems, this again doesn't matter. But let's say you had a malware detector. Can someone fool the malware detector into accepting your malware as not malware, right? Or like a traffic sign classifier. If someone somehow had access to it on like live systems, or they like changed like the sign imperceptibly, could your stop sign now look like a 45-mile-per-hour speed limit sign, right? That's bad. So like that's one of the many reasons why this is kind of a more well-researched area of SP. But the main key here is these are also imperceptibly changed inputs. Ideally, like, if your cat looks like a dog, of course it should be classified as a dog, right? But the goal is to the human eye, it should still look like what you're trying to mimic, right? But the model should still behave inaccurately. What does this look like? So really, basic example. This is a pig, right? But if you add this noise, right? This looks like nothing. What is this? I don't know. Now a model classifies it as an airplane. Hence the meeting flag when pigs fly, because with AI security, pigs fly. This is not my joke, by the way. I stole it from a very good website. It's like Adversarial ML tutorial. Amazing website, goes way deeper into the math than I can. It's written by like a very good lab, and y'all should go check it out. But I stole their joke because it's good. But yeah, so like again, that airliner pig looks like a pig, right? Like to the human eye, that's not an airplane. Okay, it doesn't look like an airplane. But because this noise that's been added to the image has been it's been created in a way that maximizes a certain model's chance of failing, right? So how do we create that noise? This isn't just like random noise that someone added. This is really specific noise that someone added to make a pig into an airplane. So how do we create that noise? How do we create these attacks? The answer is complicated. I'm going to massively simplify it. This is a very big area of research. There are like 1 million papers, each with their own different attacks. I've used like 7 or 8, like just for like various research projects that I've done. There is no one good answer, but I'm going to go over kind of the most basic ones, right? The most intuitive methods use gradient ascent. So remember how I said at the beginning that we train our AI models using gradient descent? This is basically just do the exact opposite. So instead of trying to minimize your loss, minimize your error, you're trying to maximize your error on a specific image. So this is a very good explanation. So given a 2D graph, instead of going down, we're now going back up the graph, given your input, because you want it to be wrong. And you want it to be imperceptibly wrong, but you want it to be as wrong as possible because you want this attack to work every time, right? You don't always need to have access to the model or its gradients. There are a lot of papers dedicated to showing various attacks on black box models, so models where you don't have access to like the model itself. Because like the most basic ones, like yeah, you can do like gradient ascent if you have access to the model, right? Because you can compute its gradients. You have everything you need. But what about models that aren't, public online? You can still perform these attacks. That's still possible. Attacks are also transferable, which means that attacks that work on like one model, you can often transfer to another model that you know way less about. So this is known as like surrogate models. So like if you know like roughly what data set like something was trained on, like say it was like, yeah, we use like a data set of faces. You can train your own model, knowing nothing about like the victim model's like architecture. But if you find like celebrity faces online, which is a data set, and you like train your own model randomly, and then you start crafting adversarial examples, which is like celebrity faces with some random noise added that fools your model. There's a good chance it fools your victim model as well. Just because of this is something that's been proven over and over again. But yeah, it's one way to what's up?
When you increase the loss, do you know like what specific new items to be classified as, or is it just like not the original item?
Yeah, so there are actually 2 different ways to do it. One of them you don't, one of them you do. So you can have targeted attacks, which is like, yeah, I want my pig to be an airplane. That's actually how the example I made was created. Where it was like they wanted to make the joke happen. There are also just like be as wrong as possible while still looking like the original. And both of those are valid attacks. It just depends. So like for the stop sign example that I talked about earlier, you just want it like maybe you don't want it to also be a yield sign. So you want it to be specifically, this like speed up as much as possible thing. But yeah, you can have it like you can set the class that it like works toward instead.
Is the first attack also gradient ascent?
Yeah, so all of these attacks, I will say, like, gradient ascent is the most intuitive one or the easiest to explain. There are a lot that are more complicated. But like gradient ascent, like FGSM is like the fast gradient sign method is like the actual name of the attack. But like they get a lot more complicated from there. But all of them, like a lot of them do have like targeted versus untargeted attacks. But yeah, so black box methods, like they still require some form of access to the model. Like if I have a secret model that like I tell you exists, but I don't give you any access to it, you're not going to be able to attack it at all, right? Like that doesn't make sense. So for like black box attacks, you will usually require Oracle access. So like it'll be a model that like its architecture is hidden, its data set is hidden, whatever. But you can still like submit data to the model and have it return like some form of output. Which is like the most basic form of model access, right? So like your ChatGPT, your whatever, like that's what that would look like. Where it's like you have no idea what GPT-3 looks like if you're like a casual ChatGPT user, and you have no idea what the data set is, but you have Oracle access. So in theory, like you could attack a model with like similar like access. Cool. So how do we defend against this, right? What's up? Oh, okay. How do we defend against this, right? Like these attacks exist. They might be scary depending on the models you're using. How do we defend against them? The most common defense is adversarial training. So you incorporate these adversarial examples into the training process, and try to have it disregard non-robust features, right? Because these, like the features that it's learning to like distinguish cat from dog, like in non-robust models, a lot of them aren't what we use to distinguish cat from dog, right? Like it's just noise. Because the computer can't see like eyes or like ears, right? Like that's not what it's using. It's using these like pattern matching that it's learned on like various pixels. And that's why like the adversarial attacks are so effective, is because you can now like just mess with the random noise and suddenly it's a different image. When like to us, no, it's not, right? And so incorporating these adversarial examples helps you form like stronger patterns that aren't these randomness, where it's like, hey, like maybe you want to look at the ears or like the edges instead of like, a pixel at a time. What's up?
So like, if you were to say like, for that say like, take your noise snapshot of that creates something, would it have that noise?
So I'm not entirely sure. Like again, there are some papers that say yes. There are others that are like, not so much. I'm personally like they look very identical, and they're also very compressed because they've been compressed by my slides, whatever. So like I'm tempted to say no in that case. But it really depends on like the attack you're using and like the model access you have. What's up?
And did that noise work for anything, or was it specific to that picture?
So it's specific to that picture. So I'll show you kind of how we generate it later. Like I have code for like an example. But you would have to pass every input you want an adversarial input of through your attack, in order to get like this specific attack. But yeah, so adversarial training is the most common. There are also some other ones that prevent the attacker from like getting access to gradient information, because a lot of these attacks do depend somewhat on gradient information, right? One example is defensive distillation, where it's like instead of providing, I think, like a class, you provide like, here are the probabilities of XYZ thing. And like it's basically like, how do you stop your attacker from like getting as much access to your gradients as they may have otherwise? these attacks are better than others. Like a robust model is still vulnerable to like maybe other forms of attack, how much compute your attacker has to throw the problem. Like it's all very dependent. So it's why like my answers may seem like a little like it depends, and that's because it really does. Like these are really broad like explanations of like a lot of different things. But these are like some of the most common like defenses. Kind of fun. Cool. The last category I'm going to go into today is extraction attacks. So let's say you have a private model. It's trained on private data, it's for private use. You don't want an attacker getting to it, especially because if they get to it, it could mean that they do like if they can recreate their own copy of the model, maybe they can do evasion attacks, where it's like now I can craft my own adversarial input because I have your model. Ha ha ha. Attackers can extract your model given Oracle access. So given like query access, like you can like question it and be like, hey, I have like this data set of like, a couple thousand images. Classify them for me. It'll do that, and from there you have your own data set that is exactly how this victim model performs. And you can use that to recreate a version of the model you're trying to attack. It's not going to be like 100% accurate because you don't have access to the original data set, the original architecture, whatever. But you can get pretty close, or like good enough that maybe other attacks start to do, right? Or like there are other attacks that depend on you like maybe distributing your own version of the model. So now you can say like, let's say my dog or cat model has now been victimized, right? This attacker can start distributing it and be like, oh yeah, this is a copy of this really famous dog or cat model, but it has like its own Trojan in it, where it's like given like this secret input, it can actually like this is my backdoor, so like I can maliciously classify anything I want. And you don't know about it because to you it's just this famous dog or cat model. Because you aren't looking at like the weights or biases, and like the model seems to perform accurately the rest of the time, so it's fine. So like these are things you have to be aware about, or like they can happen. CTF examples, what I'm running here for, yay. There are not too many AI questions in CTFs. I feel like I'm the only one who consistently puts them in half the time, but they're growing. Like there are a lot of examples of these out there. Like Pico CTF was like the first one I saw. I think all the way back in like 2018 or something, where they had like what was it, like tree frog or something. I forget the exact one, but they had like an evasion attack that they wanted to do. Very simple one, but so cool. So I'm going to talk through mine, but first, important tools. PyTorch and Torch Vision are just like they're the ones I use. You can also use TensorFlow. They're AI tools, like they aren't necessarily attack specific, but being familiar with them is really important, because it's how you get familiar with like making the rest of your attacks. I think Torch Vision is criminally underutilized because it has a lot of models that are already pre-trained and a lot of data sets. Like you're just doing a lot less work in a lot of these problems because they'll use common data sets where it's like, your CFAR, your ImageNet, your celebrity bases, your MNIST, and like these names probably sound like gibberish, but these are all very common data sets. And like you start to recognize like pictures from the data set after a while where it's like, if it's a handwriting sample, that's MNIST, right? And like MNIST is very, very commonly used. So yeah, get familiar with Torch Vision. Torch attacks and Cleverhans are security specific, and they implement a lot of the attacks for you. So you don't necessarily need to know the math behind like PGD in order to use it, and you should use these instead because the math PGD is annoying. But like these like they have like a lot of really good examples, and they implement a lot of the most common attacks. And it makes it like a one-liner to use. So very cool. Y'all should get familiar with these if you want to be more AI savvy with this. Yeah. Cool. So this is my challenge from CTF 2021. And it's called Pwnies Please. And the goal of this challenge was you basically had to fully model 50 times. So you were given a pony or a horse. And the goal was you had to make the models that I had running on the back end think it wasn't a horse, right? And I secretly, well, not secretly, it was in the code that I published, but there were two models. There was a non-robust model, which was vulnerable to evasion attacks, and a robust model, which I actually trained to be like decently resistant against evasion attacks because I trained in using adversarial training. And so the goal was change the image. You can't change it too much. So if you like scribble on it, it's no longer a horse, right? Like that's not an attack. That's just you scribbling on it. And the goal was like I wanted people to like attack these images imperceptibly. Like these images are also like 32 by 32 scaled up. So like attacks are a little less, you know, not like they're a little less stealth. Like you could kind of tell, but like the point was to get people familiar with like using adversarial attacks instead of just like drawing on the image, right? But yeah, you have to do it 50 times. The point was to like automate it so you could just like have one image and like spend time like handcrafting pixels. So yeah, very like I thought it was fun. But what's the solution, right? Or like what was my ideal solution? There's a lot of code I'm not showing because it's like loading a data set or like interfacing with the backend, right? Where it's like, how do you submit images? And I didn't want to show that. But at the end of the day, it's like 5 lines of code that create an adversarially generated image. So you have your criterion. That's the loss function I talked about, which is like it tells you like what's accurate or inaccurate, right? And that creates the graph that you can use. You have your inputs and your labels. So I was using a really common data set called ImageNet, which had your inputs and labels already created, right? So it could tell you like what was a horse, what wasn't a horse, whatever, right? And I like everyone who was playing the challenge knew what data set I was using. They had access to the non-robust model. Like it was all very open. So you had access to the gradients. And so you define your loss function, you move everything to the GPU, you just pass it through an attack. This is code that I have. You can also use something like torch tags, which one team actually did. Shout out IRSec. Like just given a model, your inputs, your labels, the loss function you want to use, these are just some like various parameters to like tune your attack a little further. You now have your adversarial example, and then you just pass it back to the actual challenge. You do this 50 times, you have your flag. Yay! Very simple. You don't actually need to know how PGD works. PGD is like it's FGSM on steroids, so it's that gradient ascent attack, but with like more math involved. But at the end of the day, like if you want to learn more about it, I'm happy to talk like the math of these attacks with you. I think they're cool, even though I'm bad at math. But like you don't have to know how the attack works to know that it works, right? And so now you have symbols. Well, so there's like a for loop involved in this. So like it's just generating one example at a time. It's iterating over like this test data set or like a data set of images. This was like my solution on the back end. So like what actually happened is like it was serving you images. So you get your image, you pass it through the attack, and you submit it back. And you just like do that 50 times. And it would like kind of you.
How did you prevent someone from submitting the same image 50 times?
There were so I had the image changed every time, and I had a robust model that was checking whether it was a horse, and we also had like distance metrics from like the original like the image we served to the image you like gave back, so it just like couldn't be too far off. And the images were different enough that it prevented kind of that attack. Okay.
So like if you refresh the page, given a different image,
Yeah.
you're supposed to set that.
Yep.
Okay.
So yeah, like ImageNet has like a lot of courses because it's like one of the 10 classes that it had. And I was like, cool, SIGPwny thing challenge. But yeah, I hope things start to make a little more sense. A lot of AI challenges in CTFs honestly aren't this involved because a lot of them are either like training model, which is like easy enough to do, but that's like a very different skill set. Or it's like using PyTorch as like a way to like obfuscate linear algebra, which is also like, like a thing that happens, and I have solved challenges that are just PyTorch obscures linear algebra, solve linear algebra, which you can do by hand, but this is like the most common AI security. I don't have challenges up for this yet. I will once I figure out challenges that don't involve compute and I get permission from their authors, because they're my friends and aren't responding to me. But I do intend to have like a couple challenges to like teach you how like poisoning works, and like 1 or 2 evasion challenges that y'all can play through, and I'll like kind of announce when that's available. But there are also like a bunch of them online. I don't know how many of them are still posted, which is annoying. But if I find better resources, I'll kind of like put in, like learning resources to like let y'all know. Cool. Next meetings, there aren't any. Red I forgot. Here's the flag. I don't know if okay, challenges up, flag. Thank you for listening to me. I hope y'all loved it. I'm also like, if y'all have questions, we have like 15 minutes, so.
Can you explain more about the method? Like what exactly is it? Just or can you go back to it?
No. Oh no. She's okay. Is she okay? She's breathing. If I can get her to. Aha!
Yeah.
Okay, which one?
Or yeah, the code.
Aha.
Can you explain more about the PGT method? So it's like FG, the passive gradient.
Yeah, so PGD, it's, how do I explain this one? So I use PGD because like that's what I was breaking with at the time. You can solve this using FGSM. You just like cheat. Like there was, I believe it was IRISEC that just solved it using FGSM. Because like again, my checks on like attacks were not super robust. And I was like, as long as you have the right idea, like it's fine. But it works kind of the same way where it's like there is so PGD is projected gradient descent, and so basically you're given some epsilon, that's epsilon, and like a number of steps and a step length, and that's basically how far it's going to like find an attack, and it's going to try and find a different local minimum. So it will predict dogs as cats as much as possible. And again, massively simplifying the math, but it works kind of like FGSM, where it's like they're all based around like the idea that you have access to this gradient and that you can perform gradient descent on that gradient. So that's why, if you may notice, it takes a criteria that I've defined here, and that's because given access to the model, which people had access to, and the criterion, you can generate the graphs that you use to get the gradients.
Okay, that makes sense.
Yeah. So you can't solve this via FGSM. Like that's what IRISEC did, is they just used source facts, and like they were like, we don't know anything about AI, but this worked, and I was like, cool, that's exactly what I wanted. But yeah, it's not that hard to understand. I hope. And like it gets a lot more complex from here. And like I have the actual code for PGD if you want me to show you, but it does not make much sense because I stole it from someone else. So yeah.
The data set points, general idea of how much the data set needs to be poisoned before the end.
So it depends on it depends on a lot of things. It depends on how big your GAN is. It depends on how many times it's looking at a specific thing. Data set poisoning also like it's not GAN specific. It like I was using GAN as an example because I think Poise is a very cool tool. You can do it with something as simple as linear regression. Right, where it's like given like your data, right? You have all these points. If you start introducing like malicious points, it is also considered dataset poisoning. And it just depends on like the size of your dataset and like a lot of other factors as to how it's trained. So I can't give you like a ballpark estimate really, and I apologize for that. But like at some point your GAN will fail, and on GANs that like I think the main thing with so the main thing is like with a lot of GANs, it's like you can like submit like in the style of XYZ artists. And that means that they're only training on pictures of XYZ artists at some point. So if all of them are cloned, then it'll fail to mimic that artist. So that's, I think, the main intent of pwnies is to stop like people from trying to mimic artists. Instead of like, like a generic, like it can generate images, like then your art, if your cloaked art is like one of like millions of images, right? But when it starts to be like mimic XYZ artist, then it's looking at all of these cloaked images, and that's all garbage data. So now it's 100% like fail rate, and that's kind of the intent.
So does this work against like robust models as well, the dataset poisoning idea?
So yeah, I think it depends. Because like you are creating robust. You are creating your adversarial examples based on your training data set. Because you're passing your data set through like your attack, right? So if your data set is already garbage, then like adding robustness to it won't really help because your data is garbage in the first place. So like say all your like artist images for like a certain artist are cloaked. Even if you put that through adversarial like training, it's only adding more noise to something that's already bad. So it won't like either way it should fail to mimic the purpose.
Or like, let's say you like cloaked all of your artwork. Maybe I'm misunderstanding the attack, but like, now let's say I'm an artist and I cloak all my artwork.
Right.
And then someone downloads all my artwork and they use it to, like, they want to be able to mimic my art.
Right.
But they use a robust model instead of like a non-robust model.
Right.
Will it still fail to mimic my artwork?
So the conceit with dataset poisoning is that it's like this is your new training data set, right? So like robustness is resistant to evasion attacks, which happen after your model is created. But if you give garbage data to your model, it's going to learn garbage patterns. And that comes independent of robustness to outside attack. So like it's basically failing to learn the correct patterns in the first place. So training using adversarial training doesn't really help. And dataset poisoning, like because it's being trained on these images, like it doesn't necessarily impact the robustness, if that makes sense.
Okay.
What's up?
So kind of adding on to what Pete's talking about. So pretty much if all of the data that you're giving it fails to mimic the artist, it's going to label things that aren't the artist as the artist.
Well, so GANs don't really label things. They generate new images, given like access to patterns of like a certain artist style. So it's not necessarily that it's labeling other things or that it'll label it as someone else's artwork. It's just going to be like, this is your artist painting and present that. And like, that's not it at all. So it's just wrong.
I guess like in the future, would it be possible for like we can still see that it's the original image, and I guess theoretically it's possible too for AI to like I guess ignore the randomization of the cloaking process potentially.
So maybe like I think GANs will or like people will come up with ways to defeat this attack pretty soon, honestly. But I like and like it's always like kind of a cat and mouse game. It's like you create an attack and then you figure out how to defend against it and then you create another attack, et cetera, et cetera. So like I do think that at some point like the pwnies attack will stop working, but I don't think that dataset poisoning will necessarily stop working. It's just people will have to come up with different ways to generate their data. Okay. If no one has any questions, meeting's over. Thanks for coming.